Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. We will continue making this awesome debugger, and you would like to follow along, please don't hesitate and be welcome. If you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. With that said, I would like to start by coming back to the project and see where we left off. Alright, so we got all this stuff, which is the same thing we saw here, and I believe the last thing we did was we were playing around with we continue with the REX decoding process, and we are just adding more instructions that use the REX prefixes so that we can see and test and start working with the process of it, So I think that let's open the debugger so we can see where we left off. So here you go. We disassemble REX with the B field, which goes to the RM field in this case, and we go also disassemble the R field as well and the W field as well to have 3 bits fields being used. So now the last one and the only one that we haven't checked out is the X field. So we should try to do that as well, going forward with the X field and going forward with the comes in the SIB, and the base using the SIB as well. So we're gonna have, I think we can do that today. So let's go and do both. Okay, so first of all, I would like to go and say, well, I want to have these, where is it? I'm gonna add this instruction, no, this. It looks pretty similar to this one. In fact, well, it's gonna look a lot similar to this instruction, which is move array R14, but it's just move array R12. And the funny part about that is that we found that the addressing modes in x64 and probably in x86 as well, I mean, they are like this kind of even though the first time you see them, let me show you. If I go and see the tables and I say, well, and you ask the question, well, how can you have all the addressing modes that you would normally have, or at least, let's say you have and this is a question because we haven't thoroughly like test and develop all the registered possible addressing modes. at first we thought, well, these are the only addressing modes that we have, you know, which means that that these are the registers we can use to address memory, let's say, which in a certain case scenario, well, it's gonna be just the case. Now we found that that's not the case. You know, we can use the R bit and, you know, the REX field to extend the registers to use REX registers and R18 and through 20X field. You know, all this stuff. You know, all this stuff. It's totally legit. You can use them, and it's not weird at all. You know. So we found that. So the question is, okay, so how does, in the particular case of using REXs and using R13 to R15, or even if we use control registers, which probably is not possible, or debug registers, I don't know, they should be general purpose as well. They cannot be frame point registers or anything like that. Yeah, they have to be general purpose registers because they are gonna compute memory offsets. You know, that's all this is all about, and that's pretty much the thing. You know, when you're talking about XMMM registers and stuff like that, you're talking more like this specialized register functionality that serves specific purposes. Let's say mathematics, really scientific. It can be scientific process, or it can be, I don't know, cryptography, whatever. You know, there are specific things. But for memory addressing, we don't care about that. Memory addressing goes pretty straightforward, and you can just pretty much use integer addressing, which that's what GPR addresses are for. GPR registers are for. So yeah, that's it. So the extensions that we get from the R bit are just like these specific ones, and the fancy thing is like, well, if you want to use them, for example, for R12, you know, we cannot use R12 in this case because R12 is going to R13, in fact, R13 cannot be encoded without a displacement. Let's say that's the first case we saw here. R13 has this displacement, which is 0, that makes it default to R13, so it's pretty much the same. So R12, which is using SIB, you know, it has to go and enter the SIB and tell that, you know, we're gonna have none on the index and all on the base, so you have R12 base thing addressing mode. So there are just like these specific ways to address these specific bits, with these specific registers, that makes all a change, you know. So that's what we are going for here, and this is the special case here. This is an SIB byte that encodes the R12 register for that addressing mode in that case, you know. And yeah, so if we compile that, we're gonna have a linkage error. Oh my god, which is fine. And you know, we can just go straight on and disassemble it, you know. So if we go straight down here, we're gonna find out something special about this instruction. It's the same instruction we have found and used across different stuff, you know. We're gonna have an entry, you know, the same entry, you know, same move instruction, which has an AB. And then let's say, you know, well, I'm gonna go for the mother and bar begin fetch memory operand. Well, let's go, and what's gonna happen there, because we're gonna have a memory operand there, and there you go. We're gonna have a displacement for a particular case, and then we're gonna have the displacement is gonna be null. Okay, that's correct. We have an SIB present. That's interesting. So we're gonna go and fetch the base. Yeah. Now the base size, we define it to be 8. That's correct. So let's go and say that we're going to enter. Oh my god. So here you go. We got the REX fields and we're going for the SIB. Now we haven't done anything yet with the SIB, so which pretty much you're gonna do the basic stuff there, you know, SIB by, it's gonna be something. We get it, you know, we got the index, it's 4, and the base, it's it's 4 as well. So do you have, what's the SIB by? 24, okay. Remember that we have 24 here. That means that we got 4 and 4. 4 here means none. And we are going for the 32-bit addressing forms with the SIB by there, which is good, you know. We're going through this thing, you know, which has the same idea. So this is not gonna have anything correct, you know. If we go there and we got a, you know, we have a bit scan reverse, so the info, so the rec is gonna be bananas, you know. It's RSP. That's not correct at all, because, well, we haven't done anything there yet. So let's go back into there and I'm gonna go to the register, which is here, and the idea with the SIB is pretty much the same thing, you know. We're gonna have an SIB by, we got the index, we got the base, and if we fetch the arm field, else we can do the same thing as here. If REXB now here the RM field goes for the index, if nose goes for the base, and now we don't have R here, so we don't need this to get changed, but well, I'm gonna change this to the this goes to X, this goes to B. So we have to go on towards GPR64. If we change to GPR64, we can use the bit scan reverse of the operand size to find it out, which is nice. So and in here we have to be really careful, because if you think about it, well, we cannot get from the SIB, you cannot get these entries, you know. So we have to make sure that those get null. That makes sense. And here we have a special way, which we haven't thought about, but now it's the moment. The nomenclature means that displacement 32 with no base if the mod is 00B, otherwise means displacement 32. Which is another case. But for now, let's say we have something like that. And then we don't need this anymore. Let's compile. I believe that's it. So let's see if we do it here. Now, of course, we are going towards the base. So let me go fetch me Mori. And yeah, so yeah, I mean, that was all, I guess. We're gonna go there, and the base is 4. And here we are going for that, which is the same thing, 3. There you go, that's R12. and then we push string to buffer. We have he thought we had RSP, and the reason is because I don't know why didn't we change anything here. This should be, I mean, right now we don't do anything with that. We just say that if the mod is on the I mean, for this particular case, we get 04. That means, but we're going for the RM, that means we care about this. And then we're going for the indexing, which is right here. But if you remember, we don't have nothing here. So that's pretty much the thing that now we have to care about. Because yeah, we have 8-bit thing. We're going for SIB, but in the SIB encoding we don't allow that kind of structure. So we have to deal with that stuff. Of course, this case is going for the mother and byte. It's not going for the mother and byte at all. It's going for the SIB byte because it's something that we modify here. So that's okay. We just need to deal with that special case. So for that, we can do two things. One is like, hey, we know we can make the resolution pretty straightforward and say, hey, we are not gonna get it into there, or we can just add it on to the other size, which the way the function serves us is just okay not to do it. So that whenever we go and fetch it here, we say let's see, the ones that are not possible are 20, 21, 22, 23, 24, 25, 26, 27. This goes the other way around, and just to note it. And 60, 61, 62, 63, and A0, A1, A2, A3, and E0, E1, E2, E3, E4, E5, 6, 7. That means that there's a displacement of 16 times 4, G64, so we can say so it's E so we have 0010 and then we have 0110 and then we have 0 xxx and then we have A, which is 1 0 and then 1 1 1 0. So these are the special cases here. You have to make sure. So I can make a mask here, 0x f zero or X4. Or no, I can just say that. And here I can say that. So that's pretty much it. We got the register operand, which is R12, blah blah blah, plus we didn't get anything there. Now I don't know why it returned true. Since we are not getting an index. Oh. It's like, oh, we do all this stuff and then we say, hey, result equal true. So that's kind of weird. That's kind of bad. So let's change that. Got a bug there. I don't know if we should do this, yeah. Because of the words, well, we can even more like this. This can be one of our asserts now that we're doing that in that case. Of course, I mean, one thing we can do is to pass this check as in here. Which it could be another way to go. Now, let me see. Because the SIB byte has to be checked. The SIB byte uses the same idea here, like, hey, probably we're gonna fetch towards a memory thing that has I mean, the mother byte extraction is not complete at all right now. We just have like the basis because here, for example, we just like extract blocks of it, you know. We can choose not to extract it. Well, that's what we were working at. Choose not to, but we haven't done like if we have two, you know, like the SIB byte, you know, the base plus the scale index plus the displacement, you know. Well, now I think about it, yeah, we have the displacement here, which it's something that we got from the modern by itself. So I think that's okay. You know, it's just like saying, hey, you know, if we happen to find out something like this, we don't need to or go for retching to get the fetch register open or anything like that, you know? And yeah, push string to buffer. that's it. Now we can say here as well, if index size data size invalid, that's it, and there you go. So we're gonna fetch the register operand. Now we didn't get anything, that's good. Now we don't have the plus because the index size has to change, so we don't have that there. We don't have a displacement, we push the thing, and that's all we do, which is fine, you know. We don't have that case, so we just bring it out. Now we go and fetch the register, which is our it should be R8, that's correct, and we put in the instruction move R8 R12. That's it. And C by now should be pointing towards, okay, it's pointing towards 40, which is the next instruction, that's correct. So let's see what happens now. If REX, there we go. Then we're gonna go for the entry, just a move itself again, and yeah, begin operand extraction, and and we're gonna put a plus there. We have an index, which is the case for the thing we got. We got R13 and the symbol stuff that happens because we happen to have a displacement. That's whatever. So well, probably this is like that. So there you go. That's correct. And yeah, so now we print with the SIB. Now this is kind of funny. Oh no, that's correct. Yeah, because the encoding has R12 for it, not the index. The index doesn't. We don't have an index there. You just have a base. That's the reason why we had that encoding. So that's correct. So we have to go and see. Yeah, I mean, this is all possible things. This is something that's possible as well, so it was good to disassemble it. So now we can say, let's go for the X one. Let me match it with the disassemble, which is R13, REX, RAD, REX, REX, RDX, REX, FAT, FUCOM, FLD, VM resume, PLNR, shield, add AX, door pointer, 000, move AX, EDX, okay. So all the other stuff looks pretty the same. So that's good. So I think we should change this as well. Just because, yeah. So this is in constant change, which is good. So let's try now. Let's go to Disassembling, our favorite TASM, and try to use the SIB by XB field as well. For that particular case, we will need to say, well, I'm gonna just say our let me think about this. we can have RBP plus eight times RBX times 8 plus we're just going fancy here, okay? RVX times 8 yeah, we're going here and we are gonna get a base which okay, all this nonsense. Let's see if it's possible to do. Link course so they think we have multiple base registers, so oh, okay, we have RSP and RSP. It's kind of funny. And that makes sense. So we kind of have RSP here. Well, we're gonna have, if we want to have RSP, it has to be displacement 32, so that's why we have a scale index. So it has to be this. We can have RSP here, but we can have it here. Okay, so now this is not gonna give us the XPy because that should go to the index, so in that case we need to choose something like this. Alright, so this will give us the index that we want. So if we go there and say, well, you know, I'm afraid to, no, go here and we'll see the binary. Let's see it here. Here you go. They modify the RSP, now it's going there, base index displacement. Okay, so base index displacement, and we're moving it to RBP. Okay, okay, and this instruction by itself has a mother and byte. It has 4A. That means that we have this is cool, we have where we have W and we have X on the REX. That's gonna lead us to have the index to be R15. The base doesn't change, that means we don't have to have B. We don't need that because we're using RSB. That's okay. But we need X. That's why we have the index scale. We got an index scale, and we have displacement. We have AB, which is the normal case. We have on the mother M AC. This is special. We go to here. We go for the mother M, and we're gonna have this one. Okay. We have a displacement 32, and we have RBP on the rec. That's why we have AC. And then FC is the SIB, which has to be if we go, is FC? Oh, okay, yeah. We have FC here. So this means we have EDI, which takes the place of R15, you know, plus 8, and we got ESP as a base, which is RSP. So we have RBP, then we have the displacement, which has the cumulative thing there, and then we got the whole stuff to be constructed. Which is kind of funny. So this nonsense can go to the debugger. Now this is FC, and then it goes to displacement as normal, encoded. So we can go straight down and put that into the place, you know. I mean, I don't see a particular reason not to test this, so since we are just trying to move on all the things. Now probably another cache here, like, well, we have I15, 14, 13, R12 cannot be on the SIB, probably, you know. We're gonna go for R12 times the scale, you know. In fact, let me try to do it, you know. If I say no, this is R15, R12. It was possible, so let's see how did he manage to do it. Everything's possible if you think it. So we have RSP, R12 times 8, yeah, the same thing, but now with R12, okay? So we have now for A is the same, we just have the index scale, and the index with the X field. We have AB, AC goes for the same for the mother M. That's the same, that means just that we are going to have SIB, and we have a displacement 32. That's all we know about that. So that's what AC does. And E4 now is the one that changes, because now we have E4 has to be is on the same row, because we need RSP, and it did it, you know, even though it says none, it did it. So that's kind of funny, just in the sense that even though here it says that we cannot use that field, it used it. It wasn't, I was not expecting this. It was like, well, I'm forcing you to use this thing. How are you gonna manage it? But we cannot expand it. I mean, he can. Yeah, it was like, well, what can you do, man? You cannot. I mean, you don't have another byte there, so what are you gonna do? And well, he he just did the normal thing. We just like, hey, I'm just gonna include it in the same place where you said it was not possible. So that's kind of funny, you know. Um, which is, I mean, if it's possible, it's possible. I'm not gonna blame or argue with that. Now the thing, well, what I can argue about is like, well, I mean, this probably tells me, well, that this table is just nonsense. Well, I mean, not nonsense, but that uh, let's say, for example, well, it's because if I pass E, then the mother, yeah, we need to override it, because if we say here that we have the same thing, but now with, instead of R12, we kind of pass for, I don't know, we need the same thing there. So ESP, if we pass ESP times 8, which is not possible, this is gonna be not possible. Yeah, this is not possible. So this is not encodable, but this is possible. So that's just the case. I mean, I was just like thinking, well, ESP is not possible, but R12 it's possible. So just to think about that, So let's do this, because this is gonna be something useful. We still have the we have the index, sorry, the X field down set, and the other thing is just the same thing we've done. Of course, uh, uh, yeah, and it's gonna change something that we already did there, but it was good to do it. So let me copy this. It's gonna be, well, I can write it. I'm gonna go here. It's gonna be for A. Then AB is normal. Then we're gonna have, we say that I want RBP plus blah blah blah. Yeah. Dun, dun, dun. Okay, so we need a 32-bit displacement with SIB. That means that we need AC, and here we need the SIB, which is going to be E4, and then we need the displacement, which is going to be it was this one. Well, we can put whatever here, it's a 32-bit displacement, so I'm gonna say this thing is pretty good to that. It's pretty good. Alright. So for A, B, AC, E4, 0, 0, 1, 1, 2, 2, 3, 3. And do your stuff, man. Do your stuff. You can do it. And yeah. For A, B, AC, E4, 0, 0, 4, 0, and stuff. Okay. So we do compile. Run this. And we see. So we're gonna go straight down here, you know, get the mnemonic, the same mnemonic. Go for fetch for the memory. This is gonna be interesting. The same stuff we've been doing before. We're gonna say, hey, what's going on here? We're gonna say 32-bit displacement. We don't have that stuff. We're gonna have SIB. Yes, we do. Then we're gonna say, hey, what's going on here? Now we do have that thing, so it's gonna be interesting. That's we need to change that now. We're gonna fetch the register, and we get RSP. You know, this is for the base. Which is okay. Yeah, it's RSP. And then we don't have index size, so this is all bananas and it's not gonna work. The displacement, we do have them, but it's gonna be gotten from an incorrect place, I believe. Because you were saying that the modern, yeah, this is incorrect here, so we have to change there some stuff there, because displacement is pointing towards the E4 and E4 is our SIB. So there we go. There's our problems. So let's go and solve them. Fetch memory operam. So the first thing I like to do is like, well, this thing right here, it's correct, but just for when we have something that is just calling for the index, you know, like the other one there. So the thing with that is like, we didn't encode a displacement, we didn't encode I mean, the table is telling me that it's invalid. So how in life was it possible? You know? Yeah, I mean, how can we check it for? That's my question. It's like, how do we, what's the difference between saying, let's say, you know, what's the difference between saying, I'm gonna put a simpler one, just to test it, what's the difference between saying, the one they have here, which is move whatever array R12, and let's say we have R12, which is gonna be on the base, and I'm gonna fetch it on the none, and then I'm gonna say the A scale index is gonna be times 1 for R12. Well, it's because it's R12, so you're gonna say R12 times 1 plus R12. It's a little bit wonky. Well, this is a little bit weird, but we cannot say that. But in any case, I'm saying like, well, I can just encode. It's because yeah, I mean, whatever, it can be any scale, but I'm just saying that, hey, this is the scale index R13, whatever. Yeah, I mean, what are you gonna do there? I'm telling you, hey, this is the index, okay, give me something, and this is the base, okay, this is the base. For this particular case, we have the whole thing locked. We have 4F, we have the W, that's correct. We have the R bit, yes, that's correct. We have the X bit, yeah, that's correct, and we have the B bit, okay, that's correct. AB is the same. A4 means now, oh no, sorry, 44 just means that we're going for an SIB with no displacement, I guess. Well, this tells me that there's a displacement here of 8, which is a little bit weird. Yeah, their displacements are kind of weird, like it always chooses to use this one instead of using this one. Well, I don't need the displacement at all, but whatever. And even though it doesn't use it at all, so whatever. Okay, so it's using 44, then I'm choosing 65, and 65 on the SIB. It's this one. That means I'm just choosing none in there, and I am choosing R13. So this whole thing here is just nonsense. It's like if we were looking at, I'm looking at the wrong table, let's say. It's like, hey, I have to imagine what the the extended registers for the general purpose registers will look like, because this is not the thing. We have another table at all. We're not looking at, all these things are not respected at all. We are getting R13 whenever we should get something like this, but the reason is because we are on 32-bit addressing forms, not 64-bit addressing forms. So if we go to the real thing, when we go to 64-bit, is that we're gonna have something totally different, because we're gonna have that, and we're gonna have that, and there are some of them that they are not codifiable, like the mod, for example. So, for example, this is an interesting thing. We are referencing the RSP. Yes, we are doing well. We're referencing from here. Right here, we're not referencing the RSP. So this is telling me, well, right now we have something like this. We have mod that's different 1 1. DRM is we have B plus 100. That means we're accessing the ESP. The compatibility mode operation is an SIB by prism, you know, with whatever displacement it has. Then with compatibility mode implications is that SIB required for ESP based addressing. REX prefix adds a 4-bit which is not decoded in that case. SIB byte also required for R12 based addressing. Remember this one? That we have a base addressing R12. So does this mean this means that the 4-bit base is not decoded? Okay, so if we were trying to do ESP based addressing or something, which is not something that we are doing, yeah, because right now it's just like, hey, we have this, we can say we cannot do that. It has to be this. But this is going on the base, and in the base you can do it, because on the base you don't need anything about that. Yeah, because you change it on the base, and that's possible. That's the way which is possible. You go and use ESP here in the row of the base, and you just use it as well. The problem will be like here, you know. What if we have this? Then this is not possible, you know. This is not possible because we are using RSP. Okay, that's good. Good to know, good to know. But we can use R12. And the same goes here. If we wanted to use EBP or RBP, that wouldn't be the case at all, you know. That's not possible. So yeah, the extended codes are special in that sense. So now we see what's the pattern there, you know. So we have to treat extended opcodes, extended registers, as special, and to change pretty much the possibility, if that makes sense. So yeah, I mean that's what they are meaning there. That's why I mean, it tells it that it's not. I mean, the assembler even tells us that it's not possible. So that's good for the assembler. REX reflects that's a 4-bit bit which is not decoded. Don't care. The SIB byte also required for R12 based addressing. Yeah, we know that. Now this tells me R12. I mean, this is not R12, but R12 is possible. I mean, when they say based addressing, do they mean like? I mean, it should go here, but the base is here. You know, this is RSP or R12 in the case. You know, so R12 is pretty much. I think that's possible. And RSP is just the same thing. But probably it's not decoded. So do they mean that if I use the thing we got before, I mean if we use RSP here, it's not gonna be decoded at all, because we have it here. Whatever we do with RSP is just gonna be nothing. But if we use RSP plus the bit, or do you mean? Oh, no. I know what they mean. They mean something like this. They mean RSP, or no, ESP, and then RSP. Well, it's because RSP, it doesn't make sense at all, isn't it? I mean, we've been already like not doing the wrong thing, you know. I mean, you cannot. I mean, because we make the assumption that whenever we have an R bit, that changes to RSP. Well, what I mean, or in any case, it would be like I mean, if we have the B bit for the base, that means we have R12, you know. And then if we don't have the W bit, then it means that we have this. And here it would be well, we cannot use RSPs on the index, so we can just say that we want RBP, you know, and this is gonna be EBP. What about that? There you go. So yeah, this is bananas, you know. Now this is telling me, yeah. I mean, what's that? We are on R12, the EBP times 2 or 8. Yeah, in excess 67. Yeah, I mean, it's the common case. So it was not like, yeah, I mean, this is something that we know, you know. That's good. What about this one? We have mod equals 0. That means we're going for, and we're using 101. That means that we don't use base register, not use, you know. We just use a displacement. And it means EP. And this is the thing that we found out with assembler. There's like, oh, we want to get to EVP. Well, we need to have a displacement of 0 and the mod of 1 to get the access in. We cannot access it with mod equals 0. Base register not used. EVP without displacement must be done using mod equals 0 1 with displacement of 0. And then, that's something we found that. Then we say REX prefix adds a 4th bit B which is not decoded, don't care, using RBP or R13 without it's just the same thing there. RBP or R15 without displacement must be done using mod without displacement of 0. That's something we found there. Now what about the SIB? On the index, these are the special cases. Okay, so that's good that they tells us about it, and there are too few, isn't it? I mean, it's not like a lot of special cases. We have SIB by whenever we have the index equals 0 1 0 0. That means that we have no scale, and or no index use. That's what I mean. Index register not used. Then the ESP cannot be used as an index register. That's true. ESP cannot be used as an index register. But when we have a 4-bit on B, which is REX prefix adds a 4-bit B, which is not decoded, don't care, using RBP or R15. No, we are on ESP. I was like, what? ESP cannot be used as an index. Yeah, that's correct. REX prefix adds a 4-bit B which is decoded. Now that's the thing we already found out. There are no additional implications. The expanded index field allows distinguishing. This is the thing that we were looking for. Look at this. Hold me a second. Let me. So it is decoded. So for distinguishing between RSP and R12, which is the same place, RSP is not, it cannot be used. Therefore, the expanded index field allows distinguishing between RSP from R12. Therefore, R12 can be used as an index. Hold on a second. It's because okay, let's try that. Okay, we have the problem for RSP and stuff like that. So that's for the index case. That means that if we wanna well, I can do it here, I guess. So I'm gonna say okay, Now I don't think this is gonna do the thing that I think. This is, in fact, well, we're using it on the backworks here, like RSP R12 stuff times A plus 4040. Yeah, we stumbled upon a special case scenario, RSP R12 times 8 plus 4, but it was like a little bit thing. So this is 40. 40 means that we have W, R, and X. Okay, we use W for extending to 64-bit mode. We use operand size. We use R to R8. We use X to RS. Oh, we use X, and we're using X on R12. So he thinks we are using R12 as an index, and RSP goes on the base. That means that 8, 9, 10, 11, 12. This is 12. This is possible done on the thing. Okay. Yeah, that was the thing I was expecting it to do. And now we go to mother M. It tells me it goes on 04. It's just telling me, hey, we have an SIB there with no displacement at all. Then we go to 24, and 24 tells me that we have basically that we have 24. This is it. We have R12 and RSP as the base. You know. Now, what about if I say this? Is that possible? No. So there you go. Yeah, like I was mentioning, that's not possible because then there's an option. You know, we are like forcing it to use it as the index, and it's not possible. So if I say this instead, this is possible. It's just gonna be different coding, but it's just like yeah, it was a little bit confusing, if that makes sense. So the base can be RSP, that's correct, but it cannot be index. Okay, that's a special case. And body can be R12. And that's why we got this, you know, RSP R12, we got the index, we got 24, and that's what we are decoding. So I like this one. I mean, it's simpler. Well, it's just the same thing, isn't it? This was possible because this is using the index. This is not using the RSP. And what else? Let's see. So when we are looking on the index ESP, index register not used. ESP cannot be used as an index register. REX prefix as a 4-bit B, which is decoded. There are no additional implications. The expanded index field allows distinguishing therefore R12 can be used as an index. So whenever we have in the index, we have X, then we can just go straight on. So that's pretty much what we have to do. I got you, man, I got you. So it's just like fetch, right here. So if so that's pretty much it. That's the reason why I was like, okay, so what we need, how do we feel? So I think that's it. And yeah, well, this is not W, this is X. It has to be X. So we're going from the index. The base as well has to have their own thing, like if well, I'm gonna put here to do, because the encodings for that is gonna be a whole thing there. It's just gonna do the same for, but hold me a second there. So let me see what instruction we finished decoding there. I think it was like this crazy thing, 28 take 448 thing. That's okay. It's just like we're using R12 as an index. That's possible. RSP can be on the base. That's possible. 4040. That's okay. So if that's the thing that we did, we can probably do it. It's okay. So let's do it. So we have a displacement, we have an SIB. We're gonna say, hey, what's going on here? And we got the REX. REX is telling me that has X and W. That's all we have. And let me just see the, I'm gonna go here, OX. On the instructions here, we have the 4A, AP, AC, E4, the crazy stuff. The crazy stuff, which is this one, 4A, AB, AC, E4 and stuff. Okay, so I just want to make sure. So this has a problem because it entered. Okay, yeah, I see the problem. I see the problem. It doesn't go there. This goes there. This goes there. This goes there. There you go. We got RSP, that's the base, that's correct. We got a plus there, then we have a register there, go fetch it. We've got R12, that's correct. Go fetching the thing, there you go. Oh. Oh. The scale should be 8, so there's a problem. So let me rewind here. We have scale nullify, SIB by, modern by, SIB by, well, I don't know where we are at, because we say times 8 and we have E4, yes, this goes in here. Now probably that's all busted. SIB by and 0x shift 6th. That means that we got to the scale. And then we shifted by that, and then we're gonna get 1 1, which is 3 plus 1 is 4. So yeah, this is totally busted, I think. That's not what we want. We won. We want this. Where is it? This is not correct. What we want is to use that. And shift that by that. You know? So if we shift it by 0, then we just get the scale is 1. If we shift it by 2, by 3, by 4, you know, that's what we really want. And yeah. There you go. Now we have 8. We have RSP, R12, scale 8, plus a displacement 32, which is the same thing as before. And oh, and we haven't modified the motor and by. Now it started at this. That means that over here, whenever we say, well, we know we are gonna have the whole thing, you know, we're gonna go and play around with that. We're gonna fetch a register operand, and here we have to move. This is not correct at all. Can do this. Oh, and this is so yeah, we have seen the pattern there. We have seen the pattern. We got the SIB, we don't got them. We got into there. Then we got the displacement, and there you go. The displacement has to be after the SIB, which is 0, 0, that's correct. And then we're gonna go into there, 33. So if we say, well, I don't know, byte is 33, okay, yeah, it's correct. And that's correct. Fetch register operand. Well, I don't know what it is. RBP. Is it RBP? Is it RBP? Yes, it's RBP, that's correct. Okay, that's normal stuff. And yeah, So we print instruction. We have a move RSP plus R12 times A plus displacement of 64. Well, displacement 32. Extended to 64. And yeah. Alright. So there you go, man. So let's see if we can disassemble the other instructions as well, which is, I don't remember. It's just the same move but with different stuff. This is another SIB, which is cool. For example, this instruction, if I remember, we got it there. It has to be R12 just, okay? So there you go, because we don't have REXX there. We fetch the register and we just close it. There you go. So on the output RAR12. Okay, perfect. What else? What else we got here? What else? Some crazy stuff. We got the R13 plus the displacement craziness. Okay, yeah, that's cool. So if we see this, we see R12, R13, RAX, the same thing, RAD, RAX, RDX, RAX, FF0, ST0, ST1, ST1, ST0, FLD 004, BM resume, PLINR, EAX stuff, craziness going on there. All seems fine. So that's kind of cool. Now we've assembled that special case. Now let's go one more step. Let's go and disassemble the whole stuff. I'm gonna disassemble now the other row, the special RBP cases where we have this column. We're gonna disassemble that column as well, so we can do it easily. So we know that for the base, if we have EBP, base register is in use if mod equal to 0. Okay, if because if mod equal to 0, then we don't have a base and we just have a scale index plus a displacement. If mod equal to 0, if mod equal to 1, then we have EBP as the base. If mod equal to 2, we have a base EBP and we have a displacement. Okay, so that's all, and the scale index is just the same, and here we have EBP. Now normally that's the normal thing, I guess. The only thing here is this is this special one. So first I'm gonna do it without REX, and then I'm gonna put the REX, okay, just like we were doing before. So for this particular case, I'm gonna try to use SIB without REX and stuff, without the extended thing. So I'm gonna test it with the test asm here. I'm gonna say, you know what, we're just playing around here, crazy stuff going on here. I'm gonna say move RBX core pointer and here it's gonna be let's start with the base. Okay, no base, so I want the mod to represent no base. Mod equals 0, and I want the scale index. I want our AX times I want to define the index, so I want REX times 4 plus the base. In this case there's no base, so I want this. I don't know if this is gonna do it because we don't have a, well, we have an index, we don't have a base, but we have the thing. So let's finish that. Oh my god, oh my oh no, I take it back, there you go. Okay, so that's I don't know if it's gonna do the thing that I am expecting it to do, because, well, it doesn't have base. Okay, so probably it should. Let's go. And is this one. We have RBX, RAX 4, and that thing. We have 48, that means we just have the R, we don't have anything else. Well, no, sorry, we have the W, we don't have R, nor X, nor B. So that's okay, that's the simple thing I want to see there. And I want to see AB is the same. That means that we are using 1C and 1C on the mod. It's is this thing, so it means that we are using the SIB and we're using RBX, okay? And that's the reason why we are here. RBX 1C, and you're using 85, which in this case is EAX times 4, which yeah, so yeah, it did it. Oh no, it didn't, because it's 84. Oh no, it's 85. Okay. No, yeah, it did it. It's here, you know, we're doing it from the SIB. Okay. So that means that, yeah, I mean, we are using AX times 4, REX times 4 plus displacement 32, which gives us that thing because we don't have any base. So this is the possibility to not have a base using SIB, you know. So yeah, I like that. So let's use that. And this is gonna be for 8. We're not using any registers, crazy. 0x for, this is gonna be 8b. This is gonna be C1. This is gonna be, oh, it's 1C. And this is a displacement 32, which we have the right data. So we have 48, 8B, 1C, 85. So let's see what's going on there. All right. So the same thing here. No craziness going on here. The same thing there. There you go. We have a math on the modem. For this, we know we have an SIB. We're going for the REC in the other case. So we have an SIB and the scale is 4. That's correct. SIB, base size, first moment, blah blah blah. We're not gonna have anything of this, so I mean we have a valid entry there. In fact, well, we have rex.x, but we don't have all the other cases. They don't complement. So we're gonna go there, and which, well, if you see there, we're gonna have RBP is not the thing because we don't have base, remember? So this is a special case with that. He's thinking we got RBP, which in the normal case scenario, yes, we will have that, but this is a special case and we're not gonna get it normally unless we, well, that's the base, isn't it? So it would be normally yeah and normally no. So if we go there, you know, we're gonna put SNAD there, and then here we're gonna go for REX, and then this is times 4. That's correct. And then we got displace. We don't get a displacement. We don't get a displacement. We didn't get a displacement. We don't get a displacement because that's kind of weird, isn't it? Can we go back here? Because the encoding tells me I mean, it's because the SIB tells me that we have a displacement, but the SIB doesn't have it. So whenever we have the SIB, do we do something special there? Let me see. No. So yeah, it's something that we also should change here, you know, like these are like the special cases for the SIB. um, um, where's the SIB bar here? Now we have 0x5, 0xd, 0x15, 0x1d. It's 5, isn't it? Yeah. So over here we're gonna make the thing this is not the thing. We are gonna say that the displacement data size 32-bit and that's it, isn't it? We need a displacement and the EVP. We don't need the EVP at all, you know. And yeah, that's it, isn't it? We just need this, the index, and the EVP can go whenever we don't have that kind of stuff, you know. So we're gonna have a scale index times 4, whatever, plus a displacement. So we have an invalid thing there. We have an SIP, we don't have that. We got the fields. And we have 2, 5. So yeah, probably we choose incorrectly the, well, it's correct, but yeah, let's change it a little bit, the test, because well, it's gonna be correct, just that no, because, well, yeah, it's the base, so that's correct. So REX times 4, but it's missing the displacement, isn't it? It's missing. So what was the instruction? I just got confused at there. Okay, let me see it. It was this thing where we say REX stands for plus displacement. Okay, so we have a scale index and a displacement 32, you know, and that's pretty much it. So this thing here is just that the scale can be anything, I guess. The problem is that the base has to be this, you know. If the base is blah, we normally the displacement was on the other side. So yeah, we have to just change it here as well, you know, the same thing we were doing here. We have to do it here. And we just say, hey, like this. And it's just if in this case it's going to be SAB by, well, it can be SAB fields not or scale, let's say. It's always 32-bit, isn't it? The only moment that it's not, it's with 1-1. So the only problem, so what happens here, we are not encoding that possibility. Yeah, that's the special case, isn't it? And this is using RBP, EBP, RBP, or R13. So what happens if we have the math? Oh no, because this is the math. Oh my god, okay, I was just doing it wrong. My bad. We're just thinking, hey, we have a base, blah blah blah. So this is, let me call it here, so let's transform this. And here we're using for the math, and if the math is blah 0 0, in fact we don't need anything of this. We just need to say the 32-bit. Now the special field here is that this one we got, if we got EVP. For the first case we don't get EVP, you know, so math blah 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 case 0x0 not EVP, you know, and the others are EVP. So So that's it. So that's the only case where we don't get the base register. We got an invalid thing there because RM is not 5, you know, it's 4. And then here it's just the same idea. We have 5 there and we don't fetch it. That's good. Now this is incorrect because but we're gonna change that in a moment. Times 4 and the displacement is 4. So the displacement should be pointing to 0. Okay, that's correct. And that's it, you know. And it's just pretty much the same. The only thing we have to do is to fix that thing right here. So have REX times 4, RBX blah blah blah, REP RSP plus R12 times 8 plus 0.00033221100. Move R8 R12, move R8 R13, 0.000, REX blah blah blah, REX blah blah blah, RET, REX, 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 FFF0, OB, ST0, ST1, O4, XM0, OX, EA, O4. Okay, so that looks pretty cool. So now we can do the final step and do we are almost there. We're almost there for a final, you know, to put the cherry on the cake, as you can see. We're gonna do one last one here because that's how we want it, and this one is gonna be the coolest one of them all. We're gonna have a mix of, I mean, right now we're just gonna fill everything with, well, before, I mean, it's not gonna be filling, but what we need to test is this, okay? We need to test at least the possibility of you know, this thing with x5 with an extended register, which is gonna gets us to something different. And yeah, so I mean, one pretty trivial thing that we could change here is like, well, we want to say that instead of having, I mean, we can say uh, this is possible. If we do that, we will be changing to a different thing, you know, which we have now. The only thing that I wasn't concerned about is that this is this 8, okay? So we have to change that as well. So if you want to do that, I think so the switch was the thing. Yeah, well, this we are asserting here, but I want to say mother and feel what different to this 0 1 2 3, and this can go pretty straight on here. I don't want that. Well, yeah. Yeah, okay. And that's it. Alright, those are the combinations that we care about. And now the thing here is that we have EVP as well and stuff like that. So yeah, I mean, that was pretty much the change. So what we want now, one is to test with you know, a normal instruction like this one. We say, well, this one pretty much, you know, RBP display 2. This should get in the case of 32p, you know. Okay, because I don't know if I can encode this 8, well, I can say this 8, I have it, but this has to be like that. Now probably this was not the thing we were expecting because it's 9C, and 9C he thinks we have a displacement 32, and we have RBX, that's correct, and then here we'll have 85, which is the same. We get this one because we're in AX times 4. So that's correct. Yeah. We have the scale index plus a displacement. Well, it is a 32, but we were thinking about like displacement 8, which is not encodable, but yeah. It encoded the whole 32-bit thing there, which we didn't want it. So yeah, that's correct. It was just like, well, you know, yeah, probably, I mean, this is the, yeah, I mean, it was not necessary because we already defined it to be, they're already defined to be that way. So yeah, well, it doesn't matter, we can change that later. It's just the same, we're just overwriting the same stuff. So fetch pay register. So yeah, so let's do that. And yeah, well, in fact, I don't want this, I want this. I mean, I know what the encoding should be, so whatever. So we're gonna have a 48 there, we're gonna have an AB there, then here we're gonna have I want to say this just, REP REX dispect. This is what I want. Effect. It's not gonna do it the way I want it. Yeah, but we know how to do it. We know that it's gonna be using the SIB. We want RBP, and we want 32, well, an AB displacement. So therefore we need AB displacement with RBP, that means 5C, and then we need on the SIB, I want the first one, and I want EAX la la la. That means that we need 0x05, and then we need just that. Alright, that's all we need. Right, let's go one more time, see what happens. Boop, 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 boop. Dun, dun, dun. What about the entry? We have to see it. You have a move, whatever. Here we're gonna say, hey, we're gonna have a switch. We have an A bit there. We're gonna put string to buffer. Have an SIB. Say we don't have an REX. SIB fields. XIB fields up by. You have an A bit as well. Normal stopper. Fetch register operand. We do. We have RBP here. That's correct. We have a plus. They have a REX. We don't have a scaling. We have a scaling? Yeah, but it's 1, isn't it? Yeah. So we're gonna put times 1. That's super cool. Okay. And then I'm gonna push a string there, and this is gonna be spaceman F FF. This is gonna be a Merrill FF for a long time here because it's an 8-bit thing. And then we print the last FF, and then close the brackets, and we have the right thing, you know. Got the and we have RBX, RBP, RAX times 1 FF. Okay, that's correct. If we do the same thing there, we have the same thing there. RAX times 4, blah blah blah. Now RBP, RAX times 1. That's the same thing there. Okay. So that's good. That's good. That's good. So here it comes. Here comes the last test. Okay. This is gonna be cool. Okay. This is where we join all together the whole stuff. 0x, we're gonna have 4. We're gonna have, well, it's better if I do it here. We can just have RBX as well, the core pointer. Here I'm gonna say, look, my one R13 as the base, plus a scale index, which is gonna be mm, 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 uh, is this gonna do it? I mean, I could say R12 here just as well, and it's just gonna be the thing. It's gonna be the same because it's not gonna have any problems. But R13, R12, RBX, and R R10. It doesn't matter. It can be R8 as well, or RBX. Yeah, or RSP. We're not thinking here RSP. Um, so what was happening when we have RSP? Now we have RBP. And we can have RSP there as a base. We can have it as an index. I mean, that's okay, because that's what we say here on the fetch memory. So yeah, I mean, it can be R. We cannot have here RSP. That's not possible. In fact, it's gonna make bananas. Yeah. So this is gonna. It can be R12. That's for sure. That's possible. And yeah, the other cases are just normal stuff. Yeah. We can even have REX, which, I mean, we don't see any problem with that. I'm gonna say just RDX for now. We don't care. We're gonna have a scale, whatever, a displacement, whatever, R13. The only thing that we care is from R13, and this is RBX. Compile. So we have RBX, R13, RDX stands for whatever. Okay. So we have 49. We have a base. Okay. We have a base. That's correct. We have a base that's doing that thing. We have 8B, 9C goes the same way as this one, because this is the mod RAM. We're checking for RBX, and we have a displacement 8, so that's going to be the same. This is 95 on the SIB. 95 on the SIB means that we are using EDX times 4, that's correct, and we have we don't have these at all, you know. We don't have these at all, that's for sure. So let's do that. And uh, we are gonna have an AB displacement because that's something encodable outside of it. So it should be. It should be. I don't see any reason why not to. Because on the base, register is unused if mod equals 0, but register depends on mod encoding. Adds a 4-bit which is not decoded. This requires explicit displacement to be used with EBP, RBP, or R15, which is the thing that we are using here. You see, we're using R14 plus an explicit displacement. That's the way it has to be. So does that mean that if we do this, where is it? No. If we do this, it's not possible? Is it possible? In fact, this is a better test. Okay, this is a better test. So it's simple there. This is the same. 49 AB 5C. Well, this is 5C. This is now in 9C. Because now we are not using a displacement. So model M is 5C. Let's see what happens there. Oh, look at this. We need an explicit displacement. That's why he did it that way. Even though we are not adding it, we need explicit displacement. Oh, okay. That's good to know. That was the last of our... Yeah, I mean, all these 00s that we added there is because that's the way they have to be encoded. So if you want to do that, you have to have this 0 thing here. That's the only way to do it. That's super cool. So just tell me, hey, you have a base, we have a AB, the same thing. We have 5C, that means that we have a displacement 8 and an SIB. Then we go to the SIB and say, well, it's 95. 95 is going to be something that's telling me, hey, we're going to have R13 and RDX times 4. That's what we're doing. So what about if we say, instead of this, we say RSP? That's not possible, isn't it? Oh, Jesus. That's possible. Oh my god. That's possible. Oh my god. Let's see. This is not gonna have... This is gonna be 48. Hold me a second. Are we doing the right thing here? No, it has to be RBP. RSP is possible using as the base, but RBP is not gonna be. Yeah, this tells that it's possible using RBP, but explicit displacement. So no, my bad. This was RBP. Oh, it's possible. Oh my god. Oh my god. Well, I put the times 2 so I can just see the thing, you know, which is the same here. You know, we have REP plus displacement. Well, this is not. Well, I'm gonna keep it so I can see it. So it was. So I can see the difference. So uh okay. So for this one we have 48, both is 48. We have an AB, then we have a 5C. This is just telling me, hey, we have a AB displacement, and we are having a party. We are having a party because we are using RBP. Well, now it's 5C, and 5C is, yeah, just tell me AB displacement there, go for the SIB, this SIB. This is telling me just that we have 2 times in the index scale. We're fetching for REX, and we're fetching RBP in the columns, and then we have a 0 0 there. That's all, you know. And if we want to have R13, which is the other case, we just put 49 and that's it. Okay, so that's really nice. So yeah, we can encode this. I didn't I wasn't expecting this one. This was something new to me. Okay. It's because of the special things, you know. So probably, I mean, we have extra thing to do there on the special things, but the coding this one, I'm gonna feel pleased with the thing we did today. So, okay. We have 48AB, 5C, 4500. Go and do your stuff, Mr. Compiler. There you go. And there you go. Now, if you follow the idea here, we're gonna have a base that's that. We're gonna have a mod that it's gonna tell me that we have this. It's at displacement 8, which is fine, doesn't matter. And we're going to have a base, which is correct. You know, we're gonna have, in this case, it's gonna be, we have, yeah, RBP, and then on the index side has to be done by this one. This is just fetching per example. Yeah, this is gonna be a problem because if you remember, we were saying that we couldn't. Well, this is for the index, isn't it? This is for the index. This is for the scale. So probably it's gonna work. You know, it's a weird stuff, but we need a displacement, and that's all. If not, it's just gonna be anything else. You know, it cannot be the thing. So probably it's gonna work. I don't know. We have to see. If we pass this test, we are on the other side. All right. All right. Oh my god. Oh my god. Yeah, we pass it. Ooh. Let me think. Yeah, we have RBP REX times 2 plus displacement, which it was just something stupid that I was like thinking, well, you have RBP REX RBX thing, which is the same thing. So yeah, I mean, that's the thing, you know, RBX RBP REX RBX, RBP, REX times 2, 0, and that's it. So yeah, I mean, that's encodable. That we didn't change it because we are on the RBP. So that's possible because we are going from there. But if it's 0, 0, then it's not possible at all, you know? And that's important to mention. So if the math is not greater than 0, this is not possible, you know? It will be unencodable. So yeah, I mean, it's, and we don't do anything at all to do that, you know, because we'll have problems if we do that, you know, if we didn't encode that thing. But yeah, I mean, the thing there is that there's these special cases. So we have it, we are doing it. We still have to do a little bit more polish there, but I mean, we did some tests. There are some tests that are really good, you know. Let me put it to do here. So yeah, I mean, that's it. And we can I mean, we can do the other one trivially, you know. If we put this as a 49, then this instruction has changed, you know. So if we say, well, in Disassembly, instead of doing REX times 2, I want on the base R13. Yeah, I mean, this is not totally finished. We have to polish it a little bit more to see what happens. The same instruction with a 49. There you go. Now it's R13 plus REX and 2. So yeah, I mean that works. So it can read the instruction string correctly. The only thing is that we have to make sure that the instruction string is correct. So we just have to make a little bit of a more, let's say, more robust thing where we have to test that, because the special cases have to be implemented that way, you know. Well, if we were an assembler, probably, I mean, that would be the thing to think a little bit more. But you know, we added instructions like this one, you know, all these instructions that have a 0000 are special cases for the disassembler or for the addressing modes, that they have to have this displacement to be done. So I mean, it would be pretty trivial just to nullify those, you know. But yeah, I mean, that's it. That's it. That's it. So there you go. I'm just gonna say that because why not? I'm gonna have both of them. I can do both of them. RBP or 14, RBP, RAX tends to I have the same thing done twice. That's a little bit weird. Okay, so yeah, so we have to stop here. But yeah, please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Okay. If you would like to ask some questions, please make them relative to the thing we did today, and I'll be happy to answer them. Okay. Yeah, I would say thank you very much for coming to this stream, and I will see you all on the next stream. Okay. Take care.